Late in 1944, at Camp Shelby in Mississippi, a German officer stood at a barracks window and watched an American convoy roll past on a river of asphalt, each truck humming along on rubber so new the tread still held a gray bloom, and in that steady procession he sensed an equation his staff tables had never solved. The tires came in 6s on the big transports and in 4s on the jeeps, each will a quiet assertion that the United States could keep its armies moving tomorrow just as easily as today. To a man trained to believe Allied mobility would suffocate without Asian plantations, the sight felt like a contradiction written in motion. He did not yet know that somewhere beyond the pine line and beyond the horizon of his maps, dozens of plants had been willed into existence within months, fed by pipelines of butadiene and styrene, and orchestrated to turn monomers into the black resilience his eyes now measured by the mile. Within 3 years of the emergency's first alarms, the nation would be producing roughly 920,000 tons of synthetic rubber per year, mostly GRS, and the secret behind those wheels would become the open logic of Allied logistics. The arithmetic of that abundance would not be counted in divisions annihilated or towns captured, but in engines that started, axles that turned, and columns that did not stop when the roads grew long and the winters cruel. Mississippi magnified the paradox. On any given day between 1942 and 1946, the base at Hattiesburg swelled into a city of more than 100,000, soldiers, mechanics, civilians, an organism of drills, engines, mess lines, and convoys that needed rubber the way lungs need air. Rails fed the depot, motor pools emptied onto the highway, training units cycled through with live-fire thunder and the scuffed rhythm of boots that, like the trucks, wore rubber into the ground with every cadence call. The very scale of the place, an institution that had housed over 40,000 trainees even at the time of Pearl Harbor and far more thereafter, made the quiet luxury of new tires feel like a verdict on the future. Prisoners saw it, too. Some had crossed from Norfolk on sleek passenger coaches, astonished at upholstered seats instead of slatted boxcars, their first encounter with an enemy's industrial confidence arriving as comfort. In Mississippi, the network that bound their captivity also bound the nation's strength, Camp Shelby administering POW movements as well as training, and just up the road at Camp Clinton, the highest-ranking officers of their captured armies living out a strange epilogue to campaigns that had once churned through deserts and steppes. 25 generals were housed at Clinton, a reminder that even in defeat their hierarchy survived paperwork and fences, but outside those fences the larger hierarchy, the one that ran from monomer tanks to tire racks, ruled the war's tempo. The officer at the window could not name the chemistry, but he could read the consequences. Rubber threaded through the war's machinery as surely as copper in a wire, gaskets and seals that kept oil where it belonged, hoses that did not leak in the cold, insulation that kept sparks from turning to smoke, and tires that turned a truck into a lifeline. In the air, layered rubber transformed fuel tanks into self-sealing skins that refused to bleed after a bullet passed through, a quiet reprieve granted by chemistry to a pilot who lived to turn for home. The United States was making these things in quantities that defied pre-war imagination, and the convoy outside was simply the visible edge of an invisible continent of production. There had been almost no domestic synthetic rubber before the crisis, not at the scale a global war demanded, but the shortage forced a pivot as abrupt as it was vast. Under wartime coordination, companies that had once guarded patents became partners in process and standardization, while the government financed and scheduled a latticework of monomer and polymer plants across the map. Initial facilities came online in a record 9 months, moving from blueprints to bales with a speed that turned laboratory knowledge into tires while the enemy still wagered on blockade arithmetic. Firestone produced the first bale in April 1942, Goodyear followed in May, United States Rubber in September, and Goodrich in November, a sequence of dates that the man at the window could not possibly know and yet could feel in the effortless continuity of the convoy's motion. What poured from those plants was GRS, a styrene-butadiene rubber engineered around a 75/25 formula that balanced durability with manufacturability, and whose very standardization became a weapon of reliability. From a few thousand tons in 1942 to a torrent by 1945, the curve rose until the numbers no longer measured experiments, they measured endurance. At Camp Shelby the endurance wore an everyday face. A mechanic backed a truck onto a ramp as if the tire supply were as certain as sunrise, and perhaps here it was, because behind him stood an economy that had already decided logistics would not be the reason a mission failed. Training cycles assumed better roads tomorrow because they assumed the rubber would be there, and in assuming it, they made it true. If the officer's notebooks once accounted for enemy divisions and river crossings, he now counted axles, and in counting axles he measured the thing his own army lacked more each month, frictionless replenishment. Nor was this abundance an accident of place. It was the product of a program that scattered plants for polymerization and monomer production, tying refineries to reactors, laboratories to loading docks, and contracts to rail schedules with a precision that felt almost military and yet was profoundly civilian. What began as a patch to a broken supply line became an architecture of motion, pipelines of feedstocks, reactors tuned to yields, reactors tuned to time, time tuned to convoys, that dissolved the old assumption that empires controlled resources while democracies merely consumed them. By 1945, with about 920,000 tons of annual synthetic output, most of it GRS, the program had made tires and seals into a currency of power that backed every American promise to advance. For the German in Mississippi, the contradiction persisted until it resolved into clarity. The abundance on the road was not waste, it was policy. This was how a nation declared mobility as doctrine, treating rubber as a strategic organ rather than a spare part, and supplying it accordingly. If the plantations of Southeast Asia had once seemed the choke point through which modern war must pass, then the plants of Akron, Baton Rouge, and dozens of other towns had built a new passage under the sea lanes and out of the reach of blockade. The convoy outside his window was not a parade but a solved problem, the visible answer to a question the Axis had posed in 1942 and America had answered by 1945. The equations of defeat, he would later realize, were not penciled in the casualty columns but etched in the tread that never ran out, in the oil that did not leak, in the tank that did not ignite, and in the truck that did not stop. Rubber, invented anew and made in time, had turned the thrum of 1,000 tires into the sound of inevitability. The crisis began before the fall of Singapore, in the quiet language of memos and maps that warned a continent's worth of rubber could be snatched by war and leave modern armies standing still. In June 1940, the United States created the Rubber Reserve Company to face that threat head-on, giving it a mandate to stockpile, to conserve, and to squeeze utility out of every gasket, tire, and heel until a new supply could be made from chemistry rather than trees. Speed limits were imposed to spare tread, scrap drives gathered rubber from barn lofts and city alleys, and the nation learned that mobility was now a rationed virtue. Then the worst-case map became reality. Access to about 90% of the world's natural rubber was cut off as Japanese forces overran Southeast Asia, leaving a stockpile of roughly 1 million tons to feed an economy that had been consuming near 600,000 tons per year. The gap was not a shortage so much as a canyon, too deep for reclamation and conservation alone to bridge, and too wide to trust to luck or shipping lanes. Conservation hardened into policy, tire rationing at the end of December 1941, gasoline rationing tied explicitly to preserving tires, and a victory speed on highways to slow the attrition of rubber across millions of wheels. If the blockade was a weapon, the answer would be an industry that did not yet exist at scale, and the United States moved to make one overnight by dissolving rivalries that had taken decades to form. On December 19, 1941, under the auspices of the Rubber Reserve Company, Standard Oil of New Jersey, Firestone, Goodrich, Goodyear, and United States Rubber signed a pact to share patents, processes, and information, a truce of necessity that turned trade secrets into public works. It was the document that transformed chemistry from a competitive craft into a synchronized program, and it came just 12 days after Pearl Harbor, with the urgency of a requisition order written in the nation's hand. Still, agreement was not enough. What the program needed was direction with the authority to align steel, steam, and schedules across a continent. In August 1942, President Roosevelt convened the Rubber Survey Committee under Bernard Baruch, with scientists James B. Conant and Carl T. Compton, to cut through disputes and deliver a plan in 30 days. Their verdict called for a rubber director with sweeping control and the immediate construction of 51 plants to make the monomers and polymers that would become the war's tires, seals, and hoses. The appointment came swiftly. William M. Jeffers of the Union Pacific became rubber director, with Bradley Dewey and Lucius D. Tompkins at his side, and the blueprint turned into contracts, sites, and groundbreakings in a sequence that looked less like administration and more like mobilization. Government would finance, industry would build and operate, and together they would locate polymerization units and monomer plants where rail met refinery and water met workforce. Within 9 months, initial plants were online, a construction tempo that collapsed the distance between laboratory protocol and the thrum of production floors. While tires were rationed and speed limited, the back end of the system learned a new rhythm. the cadence of continuous reactors, delivery timetables for butadiene and styrene, and a standard, mutual recipe, for GRS that made every bale predictable and every tread dependable. Rationing on Main Street and breakthroughs in Akron were two sides of the same coin, paying forward reliability to the convoys that would leave training fields and shipping docks for the long roads of Europe and the Pacific. The point was never austerity for its own sake, it was the deliberate transfer of wear and tear from the front lines to the home front, where a slower drive and an older tire bought another week of mobility for a division. The scale of the undertaking defied the old logic that monopolies guarded capacity and patents guarded pride. Here, pride was measured in uptime and yield, and capacity was scattered on purpose, plants sited far from bombers' flight times and close to pipelines, spreading risk while concentrating output. The Rubber Reserve Company kept its ledger in long tons and lead times, while the War Production Board and railroads made sure what left a monomer unit found its way to an emulsion kettle without waiting for a miracle. Scrap drives, meanwhile, were more than theater. The Library of Congress files show programs like the Idle Tire project asking citizens to hand over unused rubber to buy time as the new plants rose, and the country answered with a generosity that read like a vote of confidence in chemistry. It was a bridge of weeks and months built from garden hoses, old boots, and raincoats, enough to steady the military's pulse while steelwork climbed, foundations cured, and pipefitters laced America together with valves and gauges. In that interval, the nation learned to live with fewer tires so that the new ones could be born in the thousands each day, an exchange that turned patience into production. By the end of 1942, the first GRS bales had already rolled from Firestone, Goodyear, United States Rubber, and Goodrich, small numbers at first but unmistakable as proof that the plan worked. The curve that mattered was not abstract, it was the slope of daily output against daily need, and each week brought more capacity under steam, more railcars of feedstock, more batches that met the standard without drama. The convoy glimpsed at Camp Shelby would be the last mile of this effort, not its sum, and its assurance would be earned in 9-month miracles happening far from any parade. When historians later summarized the program as 51 plants built at record speed, it captured the administrative triumph but not the lived one, the way ration books, factory whistles, and patent pools became a single instrument tuned to mobility. The program's genius lay in turning a shortage into a system, where every conserved mile on the home front produced an extra mile at the front, and every solved engineering problem sent a little more endurance down the assembly line. What blockade tried to deny, organization supplied, until the very idea of running out of rubber felt less like fate and more like a problem that had already been solved somewhere upriver. By early 1943, the canyon between need and supply was narrowing, and the nation had learned to translate sacrifice into throughput with the fluency of a logistics officer and the stubbornness of a commuter still driving on ration tread. From that point forward, the story would be told in capacities, yields, and lifetimes, less about whether rubber could be made at all and more about how well it would perform under heat, cold, and speed. The crisis had not ended, it had been transformed into an industry, and the war would now measure victory not only in battles but in bales. The plan touched steel the day chemists' recipes became construction schedules, and from that point the United States stopped talking about shortages and started making rubber in bales that could be loaded onto flat cars and turned into the quiet geometry of tires, seals, and hoses. The first bale came from Firestone on April 26, 1942, followed by Goodyear on May 18, United States Rubber on September 4, and Goodrich on November 27, for milestones that announced a new industry had crossed from resolve into throughput. At first the numbers were modest, just a few thousand tons in 1942, but the line on the chart was not a plateau, it was a slope, and by 1945 annual production stood at roughly 920,000 tons, with about 85% of it the general-purpose war workhorse known as GRS. The bales were more than rubber, they were proof that a nation could translate chemistry into logistics with the speed of a mobilization order. GRS had a virtue far beyond mere substitution, it was standardized, typically a 75/25 butadiene to styrene copolymer that tire makers could trust would behave the same from one plant to the next and from one railcar to the next. Standardization begot reliability, and reliability begot scale, because the men and women running mixers, calendars, and curing presses could set their gauges for a known material and expect the same cure curve shift after shift. Behind that dependability stood an architecture of plants designed and brought on stream in a record 9 months, financed by government capital and operated by private firms that had agreed to share patents, data, and engineering as if the line between competitors had been erased by necessity. The result was neither purely public nor purely private. It was a deliberate alliance that turned geographical sprawl into resilience and technical consensus into a production tempo the enemy had not imagined possible. Inside those plants, emulsion polymerization transformed liquid butadiene and a water emulsion of styrene into latex, a finely dispersed sea of polymer particles that would be coagulated, washed, and dried into 75-pound bales ready for shipment. Operators monitored Mooney viscosity, the practical language of a compounder's day, to ensure each lot hit the specified plasticity, making GRS not only abundant but predictable under the stresses of mixing, extrusion, and vulcanization. Coagulation and drying practices varied among facilities, but the process discipline did not. It was the same story repeated from Akron to Lake Charles, a choreography of tanks and trains that made engineering consistency the backbone of an army's mobility. To the war's accountants, the beauty of GRS was that every bale could be planned for, every batch ticket meant the next tire would cure like the last, and every cured tire meant another truck that did not wait on a dock for miracles. Feedstock was its own campaign, fought in pipelines and columns of tank cars that carried the monomers where they were needed, often from plants located by design near refineries and rivers. In 1944, about 64% of U.S. butadiene flowed from quickly built facilities dehydrogenating grain alcohol, a stopgap that proved decisive until petroleum routes scaled, while parallel investments in styrene capacity from firms like Dow ensured GRS did not starve for its second monomer. The siting choices, polymer plants here, monomer units there, were not arbitrary. They were a risk management map drawn across a continent to keep the reactors fed regardless of weather, accidents, or wartime hazards. Each integration decision, what to build where and how to connect it, paid off in the only currency that mattered, bales per day that arrived where the tire presses stood waiting. Wartime necessity also accelerated process refinements that tightened the link between laboratory theory and factory floor reality. In 1944, producers began adding carbon black slurry directly into GRS latex before coagulation, an innovation driven by finishing bottlenecks that had the side effect of improving dispersion and giving tire makers a head start on the reinforcement that turned rubber into roadworthy tread. Measurement and control advanced in parallel. Mooney plastometers, batch tracking, and reactor train control schemes turned what could have been artisanal variation into industrial consistency. These incremental improvements, made under pressure and at speed, mattered as much as the headline numbers because they made scale sustainable. The emulsion lines themselves, cascade reactors tuned for conversion, stability, and heat removal, became the pulse of the program, marching latex through trains of vessels that had to be both robust and forgiving to hit targets shift after shift. Operators aimed for composition and molecular characteristics that compounding in service demanded, knowing that a tire's life began with the kinetics in a reactor as surely as with the cure package on a press. What emerged at the end of the line was not a scientific curiosity but a production-grade material that tempted fate not at all. It behaved, it mixed, it ran, and it wore in a way a quartermaster could plan around. In an army of moving parts, predictability is a kind of mercy, and GRS delivered it. Low-temperature emulsion polymerization, cold rubber, would soon prove its value by yielding SBR with fewer branches and better mechanical properties, a direction of travel set in wartime research and entrenched in the immediate post-war years as plants and recipes adapted. GRS did not simply replace plantation rubber, it made a new promise to the war effort, that mobility would be a function of planning and plant maintenance rather than the map of Southeast Asia. Which is why, by war's end, the totals mattered less than the tempo, the bales flowing from polymer lines were the metronome to which an army moved, and the rhythm did not miss a beat. IG Farben's answer to blockade was Buna. Coal turned into elastomer behind factory walls at Shkapa and Hulse, promising independence from trees and ships, but delivered on a timeline too slow and a system too brittle for a war that moved faster than commissioning schedules. At Shkopau, where the foundation stone was laid in 1936 and production began in 1937, the Reich guaranteed prices and credits to scale a plant that became the centerpiece of German synthetic rubber, yet even at design capacity it remained a single organ in a body vulnerable to every cut in fuel, hydrogen, and transport. Pulse joined the program in 1939, another node in a chain that looked formidable on procurement charts, but whose throughput depended on utilities and feedstocks flowing across a network that Allied planners would soon learn to break. The chemistry worked, the calendar did not, because each month of construction and each day of maintenance existed inside an air war that treated every coking plant, hydrogen unit, and refinery as a lever against rubber itself. The boldest wager rose at Auschwitz-Monowitz, where IG Farben chose Oswiecim for a vast Buna and fuel complex beyond easy bomber range, near water and coal, and lashed to rail, then bound the complex to a new camp, Auschwitz III Monowitz, to extract labor at the point of a gun. The plant's construction consumed tens of thousands of prisoners, overwhelmingly Jews, driven under SS guard to pour concrete, raise pipe racks, and align columns for a factory that, in the end, never made usable rubber for the Nazis before the Red Army arrived. Bombing raids in 1944 struck the complex while it was still being fitted out, killing prisoners and workers and delaying startup cycles that IG planners optimistically projected into 1945, a schedule overtaken by the front itself. Monowitz stands as the starkest ledger entry in a program that mortgaged human lives for an output that never materialized when it was needed, proving that terror is an engineer's worst process control. Across the Reich, the Buna network's best year arrived around 1943, with Shkopau rated at thousands of tons per month and national totals peaking before declining under compounded shortages, degradation, and attack. The United States Strategic Bombing Survey traced the mechanism of collapse. Hulls shut for a month after a June 1943 strike, took 3 months to reach 72% of capacity, and 7 months to recover fully, only to be throttled again when Ruhr's synthetic oil plants feeding its gas were knocked out in mid-1944. Shkopau's dependence on hydrogen from Luna turned a blow against fuel into a blow against rubber, as interruptions in hydrogen cascaded into lost output regardless of how intact the polymerization trains appeared on aerial photos. By late 1944, overall production had fallen sharply from earlier highs as oil, power, and transport shocks turned nominal capacities into fiction and forced plants into a stuttering cycle of restarts, repairs, and shortages. Inside IG Farben's monopoly, knowledge flowed vertically but guarded, a corporate logic at odds with the wartime need to diffuse solutions laterally across multiple firms and sites, which is why process improvements lagged the tempo that Allied air power imposed. The group's concentration of decision-making amplified single-point failures. When specific utilities, catalysts, or units went down at key sites, the absence of a broad, standardized peer network limited the ability to substitute capacity quickly. In contrast to systems built on open patent pools and interchangeable standards, Buna's architecture remained centralized and personality-driven, which made it swift at decree but slow at adaptation when reality refused to obey plans. Industrial chemistry thrives on discipline and feedback. Secrecy and coercion made both scarce, and the result was drift, yields that wandered and schedules that slipped in the shadow of sirens. The human cost at Monowitz framed the moral and practical bankruptcy of the model. Auschwitz III supplied the workforce for IG Auschwitz, and testimony and archives record that prisoners were selected, driven, and often killed by labor faster than any stable production regime could be established. The factory's completion in January 1945, just as Soviet forces approached, meant the complex stood as a nearly finished shell over mass graves, a monument to a 500 million Reichsmarks squandered in cruelty and delay. Wherever the paperwork claimed capacity, the lived reality was starvation rations, disease, and beatings, conditions that destroy the cleanliness, calibration, and continuity that continuous polymerization requires to deliver specification rubber. Even beyond Auschwitz, the broader synthetic program labored under the physics of Germany's late-war economy, where each missing railcar of coal or cracked reformer tube choked downstream plants that could not localize their risk. The USSBS summary makes clear that the rubber sector, though not always a priority target on its own, suffered decisively from the attack on oil and associated chemical systems, proof that a chain can be strangled at any of its vital organs. When utilities faltered, polymerization trains stood idle regardless of how many vessels were intact, and when transport failed, finished product and critical spares stranded where they could not help. Thus the graph of German synthetic rubber shows a crest followed by steps down, each step a shock that the system could not amortize under sustained attack and mounting scarcity. After the war, Schkopau's plant would be expropriated under Soviet administration and folded into Chemischwerke Buna, a socialist combine that kept the chimneys working in a new world, an echo of what the complex might have delivered had it not been built to serve a regime at war with human life. The Buna story therefore reads as both technological achievement and strategic failure, chemistry that could make rubber from coal, embedded in a logistics and labor system that ensured its promise arrived late, fragile, and thin. When Allied trucks rolled on plentiful tires, they carried more than troops and fuel, they carried the verdict that collaboration, standardization, and free labor outperform monopoly, secrecy, and chains. Germany's synthetic rubber peaked too early, fell too fast, and learned too late that in modern war the factory is only as strong as the society that staffs it and the arteries that feed it. They expected a rattle and sway in boxcars and instead stepped into a polished passenger coach at Norfolk, surprised by upholstery, ice water, and the hum of a train that carried them across a continent they had only fought in maps. Days later, the line ended at Camp Clinton outside Jackson, Mississippi, where barbed wire cut the horizon into squares and barracks rows, and where, for the first time since capture, surprise gave way to routine, regular meals, organized work, and an order that felt less like punishment than a careful accounting of days. Most were Afrika Korps men taken in Tunisia after the spring collapse of 1943, marched through Algerian cages, shipped to Virginia, and then parceled across the South. In their diaries the shock is quiet but unmistakable, not savage guards, but a sleek train, not deprivation, but a schedule that fed them 3 times a day. It was not mercy so much as confidence, an assertion that the United States could hold an enemy humanely and still wage a total war, and for soldiers trained on scarcity the lesson arrived as comfort they had not expected to feel. Clinton was unusual, and everyone on both sides knew it. The camp housed some 3,400 POWs and, uniquely, about 24 generals and admirals, men who had once signed orders with sweeping arrows and now signed for linens and library books under the Geneva Convention's exacting reciprocity. Hans-Jürgen von Arnim, who had succeeded Rommel in North Africa, lived there along with other senior officers such as Ferdinand Nolling and Dietrich von Koltitz, their rank acknowledged even in captivity by separate housing and small privileges that could not disguise the fact that the war had moved past them. Where a general once moved armies, he now saw wheelbarrows lined up for a day's work, and the contrast taught its own doctrine. In this country, even the defeated could be set to useful tasks inside a larger plan. Useful, and vast. The U.S. Army Corps of Engineers had long dreamed of a working model of the entire Mississippi River Basin, a 1 square mile landscape calibrated to water and time, and Camp Clinton provided the labor to carve it into the earth outside Jackson. German prisoners cleared the site, dug drainage, poured channels, and assembled miniature bridges with a precision that mimicked the larger engineering of a country bent on making the continent's rivers themselves measurable and governable. What they built, under guard, for pay, and with shovels and forms, was a model of how the United States thought about scale, that even the Mississippi could be tamed by calculation if enough hands did the work in sequence. Around Mississippi, camps multiplied like waypoints on a logistics map, McCain near Grenada, Shelby near Hattiesburg, Como in the Delta, each a node connected to branch camps feeding labor to farms, forests, and public works. On the Delta's flat horizon, prisoners hoed and picked cotton by hand, dragging canvas sacks through heat that felt like the desert again, while in the pine lands others planted seedlings, cut pulpwood, and cleared rights-of-way, a landscape of work that taught the geography of a country in motion. At Camp Shelby, a base that trained tens of thousands, POWs were folded into the same rhythm of reveille and mess lines, the camp newspaper even reporting athletic scores inside the wire, an echo of normalcy curated by rules the Germans had not expected to be followed so precisely by a wartime enemy. What began as captured manpower became a labor market with hours, wages, canteen purchases, and a steadying predictability that kept resentment at bay and routine alive. The Geneva Conventions were not abstract to the men in the barracks, they were breakfast menus and sick call, dental chairs and soccer tournaments run between barracks teams under a hot Mississippi sun. The food was good and abundant by the standards of Europe in 1943, cereal and coffee in the morning, meat and vegetables at lunch, bread and milk at night, and the cooks were often German, working with American supplies that seemed inexhaustible to men who had learned to hoard. Library shelves and English classes filled afternoons not assigned to work details, and the small economy of an 80-cent daily wage and canteen cigarettes provided the familiar ballast of routine that did not depend on victory or loss. Even uniforms were managed with ceremony and pragmatism, parade tunics for funerals and holidays, stenciled PW, khaki for every day, wool in winter, athletic shorts for games, all of it catalogued and issued with a bureaucratic care that felt like a promise kept. Yet inside the wire, not every hierarchy dissolved. Fanatical Nazis coerced and punished fellow prisoners, and at Camp Clinton a German soldier was murdered by hardliners, a crime that forced American authorities to intervene and transfer the ringleaders to special camps in Oklahoma where their menace could be contained. Escape attempts surfaced like ripples, tunnels lit with scrounged bulbs ending 10 feet shy of a fence, walk-offs from fields that proved futile once money, clothes, and accents betrayed their authors, but most men did the arithmetic and chose to wait out the war alive. The paradox held, it was easier to slip away than to disappear, and easier to endure than to outrun a country whose trains and roads seemed to gather runaways back without effort. Across an ocean and a different system, another kind of listening was underway. At Trent Park in North London, MI-19 built a secret listeners' house, lacing rooms with microphones and staffing rooms with German Jewish émigrés who could transcribe every dialect and technical aside from high-ranking POWs held in comfortable captivity. The operation collected a trove of candid intelligence, weapons programs, unit morale, and the first chilling accounts of mass murder, all mined from conversations that officers never would have offered under interrogation yet volunteered to the air when they believed they were alone. There is a parallel between the two systems of custody, one American and one British. Both treated captured men in ways designed to yield order, labor, or information, and both revealed as a byproduct how deeply the Allies trusted organization to do the work that cruelty could not. For the German enlisted man assigned to fell pines near Picayune or hoe rows outside Belzoni, the lesson was intensely local, that a nation could be vast and yet run on schedules, that a prisoner could buy a beer in a camp canteen, that a library book and a soccer match could coexist with the knowledge that the front was moving far away. For the general and Clinton eating in a separate mess, the lesson was more strategic, that even rank could be made procedural, respected as a category while stripped of power, and that the same country that ran passenger trains for prisoners could commit engineering armies to pour a model of the Mississippi into a field. Both learned, day by day, that their captors' strength lay not only in factories but in the reliable repetition of small things, forms filled, meals served, rails kept, until the repetition itself became an argument about who would endure. And through it all, the America they moved through in guarded columns remained stubbornly itself, lawful to its treaties, methodical in its uses of labor, and rich enough in systems to absorb enemies and turn their days into measurements of its own confidence. By the time news filtered in of fronts collapsing and cities burning, the Mississippi seasons had already taught the prisoners the shape of their captors' power. It was not only the size of its factories but the steadiness of its institutions, a steadiness that could put a spade in a Pau's hands and a book on his bunk and consider both part of a victory measured in months. When they returned home in 1946, some after nearly 3 years in the States camps, they would tell stories of a war that ended for them on passenger trains and in model rivers, of a captivity that was less a humiliation than an education in how their enemies organized the world. And in archives and memoirs the record of Trent Park's clandestine rooms would stand beside the Mississippi River Basin model as complementary exhibits of the same truth, that Allied power, at its core, was an architecture of listening and labor that built advantage by accretion rather than by spectacle. For men who had believed logistics could be starved into silence, the quiet routines of the camps delivered the final argument, that abundance, systematized and patient, speaks softly and carries a very long line. They called it cooperation, but it felt like orchestration, a nation turning competitors into partners, laboratories into supply lines, and patents into recipes that any qualified engineer could run at a new plant brought to steam in 9 months. On December 19, 1941, Standard Oil of New Jersey, Firestone, Goodrich, Goodyear, and United States Rubber signed a patent and information sharing pact under the Rubber Reserve Company, a truce that converted trade secrets into common standards for a single mission. Within weeks, committees convened chemists and engineers from government, industry, and universities, Akron, Princeton, Chicago, Minnesota, so that process fixes and analytical methods moved laterally and instantly instead of climbing corporate ladders. More than 200 patents worth of findings, on polymerization control, modifiers, carbon black specifications, and butadiene efficiency, were pooled, turning private breakthroughs into public capacity. If the pact supplied the recipes, the state supplied the steel. Through the Reconstruction Finance Corporation's Defense Plant Corporation and the Rubber Reserve Company, Washington financed and owned 51 synthetic rubber facilities, then leased them to private operators, often at a nominal rate, to run at speed under War Production Board allocations. Plants were deliberately scattered, some to make monomers, others to polymerize, so that feedstocks, water, and rail converged while risk dispersed, and so that a shock to one node would not silence the whole. The mandate was simple: industry would build and operate, government would pay and coordinate, output would be standardized so that a bale from Lake Charles could cure as surely in Akron as any other. Personnel mirrored policy. B.F. Goodrich engineers such as W.I. Burt and Walter Piggott chaired plant design and production engineering committees, writing the common playbook that let different sites hit the same targets with the same gauges and controls. The Copolymer Research Committee met from December 1942 onward to align lab results with factory constraints, ironing out kinetics, molecular weight distributions, and quality control so that Mooney numbers and cure curves matched what tire makers needed in practice. Academic partners sharpened the instruments, better analytical methods, clearer understanding of emulsion kinetics, and a shared language for defects and dispersion that operators could apply in real time. Standardization was strategy. GRS, styrene butadiene with a typical 75/25 recipe, became the interoperable backbone of the war's rubber, its predictability enabling mix rooms and curing presses to run with minimal retuning as bales arrived from multiple plants. Because the recipes, additives, and analytical checks were aligned across firms, quality drift narrowed and throughput stabilized, which is why early trickles in 1942 became a reliable torrent by 1944-45. Uniformity did not mean stagnation, it meant every improvement, on modifiers, carbon black handling, monomer purity, propagated through the network quickly rather than being trapped inside a single company's walls. Finance underwrote tempo. Defense Plant Corporation funds covered concrete, columns, reactors, and utilities without waiting for bond markets or board approvals, while leases and operating contracts guaranteed that capital met competence on a stopwatch, not a calendar. Expenditures ran about $2 million per day at the program's height, with total facility costs around $700 million, and the administrative design ensured that money translated into installed capacity instead of litigation over who owned which patent. The same framework handled research contracts with universities and private labs, making curiosity a budget line in a production program. Logistics was built into the blueprints. Siting put monomer plants within rail reach of polymerization kettles, and polymer plants within scheduling reach of tire makers, so that tank cars and boxcars could be planned as extensions of reactors rather than afterthoughts. Because the government controlled allocations, balancing demand from military priorities to civilian rationing, the system could flex without starving critical users or letting finished stockpile idle in the wrong place. In a war won by timetables as much as tactics, this administrative spine gave chemistry a clock to keep. The result showed up first as symbols: a Firestone bale on April 26, 1942, Goodyear's on May 18, United States Rubbers on September 4, Goodrich's on November 27, and then as statistics that changed strategy. From 2,241 tons in 1942 to about 920,000 tons per year by 1945, roughly 85% GRS, the curve can be read as a measure of how fast collaboration compounds when ownership questions are answered in advance. Every added plant was not just more capacity, it was another vote for uniformity, another proof that the pact and the leases made different operators into one machine. The convoy rolling past a Mississippi barracks window in 1944 was the last link in a chain whose first links were signatures on a December document and appropriations pushed into steel without delay. The political economy mattered as much as the chemistry. By combining public capital, private operation, and mandatory knowledge sharing, the program neutralized the two classic bottlenecks of emergency industries: underinvestment and fragmentation. It also created an institutional memory, reports, standards, and routines, that could be handed back to private hands after victory without dismantling the know-how that made it work. When the government sold the plants in 1955, it did not retire an experiment, it completed a loop in which the state had created an industry at speed and then converted it into a durable market. Cooperation did not mean consensus without friction. It meant a framework strong enough to absorb disputes without slowing output. Differences over feedstocks, reactor trains, or testing protocols were resolved in committees and standard updates, not by delay, because the mandate to share replaced the incentive to hoard. In that sense, the architecture of collaboration was itself a weapons system, a way to turn every solved problem into everyone's solution by the next production cycle. And because the leases and allocations made production a national project, the victory belonged to the system rather than to any single firm's glory. This is why, by late 1943, the question had shifted from, "Can we make rubber?" to, "Where should the next bales go first?" A question of logistics, not possibility. What began as emergency improvisation had become an institution: cooperative research, standardized recipes, financed construction, leased operations, allocated output, and the calm cadence of reactors that did not care which logo was on the gate. The Allies' advantage, visible in every fresh tire, was not a single invention but an agreement to agree, and then to build that agreement into steel, schedules, and the dependable weight of a 75-pound bale. In the end, the most radical chemistry was social, a design that made rivals interchangeable, knowledge transferable, and production inevitable. Rubber is the quiet anatomy of war, the unseen organs that move, seal, cushion, and protect, turning steel and fuel into motion that lasts long enough to matter. It exists where no one looks, under tires, inside pumps, along fuel lines, clamped between engine casings, and every mile an army makes depends on how well those hidden parts resist heat, vibration, and time. When the United States decided to make synthetic rubber not in batches but in bales and then in railcars, it wasn't just solving a material shortage, it was giving the war a circulatory system that could not be blockaded. Start with tires, because everything else starts there too. A truck that carries rations or ammunition is only as real as the tread that keeps it on the road, and a convoy's promise is only as good as the compounds that survive heat, cold, and load. GRS, standardized, predictable, abundant, allowed motor pools to plan maintenance instead of improvising it, to trust that a replacement tire would behave like the last one, and to keep columns moving in mud, snow, and the hard sun of summer roads. Then consider what tires don't show: the gaskets and seals that keep oil inside engines, the hoses that ferry fuel without weeping, the electrical insulation that refuses to arc in rain or spray, and the vibration dampers that stop metal from tearing itself apart. All of that is rubber, And all of it was produced in quantities that let mechanics swap parts instead of cannibalizing them, a luxury made mundane by the reliability of GRS across suppliers and plants. What looks like equipment endurance on the line is, in truth, material science refined into schedules and spares. Now move to the air, where chemistry turned mortal holes into survivable wounds. Self-sealing fuel tanks layered rubber and treated sheets so a bullet that pierced the wing left a wound that swelled shut, a slow, stubborn seal that bought minutes and sometimes lives. Bombers like the B-24 flew with multiple rubber fuel cells, 18 in some configurations, whose self-sealing construction turned a single tracer's path from catastrophic fire into a manageable leak. Across aircraft types, the principle was the same, layered elastomers, designed to swell on contact with fuel, closing ruptures before flame could do the rest. Rubber also defined the sheer mass of modern war machines, a measure few civilians ever saw on paper. Building a military airplane took roughly 1,000 pounds of rubber, a single tank needed about 2,000 pounds, and a battleship demanded on the order of 75 tons, numbers that explain why replacing plantation latex with GRS wasn't optional, it was existential. When economies of scale finally arrived in 1944, with hundreds of thousands of tons of synthetic output, those tons became not abstractions but fleets. Engineers didn't merely copy nature, they exploited process to shape performance where it mattered. Uniform GRS recipes and quality control meant tire makers could calibrate cure cycles for tread life and heat resistance, while hose and gasket manufacturers could tune hardness and elasticity for the temperature windows of engines and hydraulics. Consistency let factories treat rubber as a design component rather than a variable, which is why replacement rates stabilized and equipment tempo accelerated without hidden penalties. On the ground back home, the same material was rationed with a moral clarity that linked towns to troops. Tire rationing began on December 27, 1941, the first non-food item to be restricted nationally, because conservation of civilian tires was the only immediate way to buy time for the synthetic program to come online. Gasoline rationing followed with an explicit purpose, to reduce driving and thus preserve rubber, while a nationwide victory speed of 35 miles per hour lengthened tire life by law more effectively than any poster could. People saved rubber in ways mundane and patient, fewer trips, slower roads, recapping when possible, so that trucks overseas could be shod with new tires without apology. Rationing wasn't deprivation for its own sake, it was a transfer of durability from the home front to the front line. Every mile not driven in Ohio left a few grams of tread on an American tire somewhere else, and multiplied across millions of cars that arithmetic became convoys that didn't stop. Scrap drives collected garden hoses, galoshes, and worn-out tires not because they were a perfect feedstock, but because they signaled a shared willingness to bridge the months between plan and production. The synthetic rubber program gave commanders options they could trust in their bones. When a division quartermaster knew that a requisition for tires would be filled with material that cured the same and wore the same, he planned differently, more ambitiously, because the worst unknown had been removed. Reliability is strategy by another name, and GRS made reliability scalable. In the sky, that reliability kept airplanes from burning and kept them flying long enough to bring crews home. Self-sealing tanks were not perfect, they added weight, and sometimes they failed, but across campaigns, they were the difference between a whole and a funeral, and they did so by design rather than by luck. The United States invested not just in the tanks themselves but in the supply chains that kept rubber components for aircraft, seals, bladders, lines, available as routine replacements rather than rare privileges. Ships, too, became floating catalogs of rubber parts that never made the news. From hatch gaskets to shaft seals, pump diaphragms to cable insulation, elastomers kept seawater out and fuel and power where they belonged, extending operational readiness in a theater where salt and vibration punished carelessness. No headline ever praised a gasket, but 1,000 such quiet victories made voyages possible without drama. The paradox of rubber in war is that its heroism is invisible until it fails. A blown hose or a brittle seal turns into flames or silence, but a compound that endures becomes a footnote, logged as operational rather than miracle. The synthetic program embraced that humility, engineering a material that would vanish into systems and make their success look ordinary. Meanwhile, on Main Street, ordinary was the point. Citizens accepted tire inspections, ration books, and speed limits not because it was convenient but because it was comprehensible. Fewer miles here, more miles there, all counted in the same ledger. It's why even when synthetic output surged in 1944, rationing persisted. The last miles of the war were still the hardest, and the margin of safety was measured in inventories that were never allowed to run dry. By 1945, the system had done more than catch up, it had redefined what enough meant for a modern military. The capacity to make GRS at scale, to keep aircraft tanks from bleeding fire, to ration without panic, and to deliver standardized parts across oceans translated directly into a new kind of momentum. Mobility ceased to be a question and became a given, and from that certainty, strategy could stretch farther and strike faster than any enemy's arithmetic had predicted. There is a final symmetry in the story that matters. The same country that limited speeds to 35 miles per hour to save civilian tires also made rubber that allowed bombers to come home after being shot full of holes, and the same hands that surrendered a ration coupon took quiet pride in the miles those coupons bought at the front. Rubber did not make headlines because it made outcomes, and outcomes are what history remembers when the noise has faded. By 1943, the slope of the line no longer looked like hope, it looked like capacity, and by 1944 it had become tempo, the steady beat of reactors and railcars that turned chemistry into miles at a scale no blockade could touch. What had begun with the first cautious bales in 1942 now flowed in volumes that made planners speak of installed capacity, rather than shortage, because the country could finally promise rubber not in shipments but in schedules. Annual production would reach about 920,000 tons by 1945, and with roughly 85% of that as GRS, the war's general-purpose workhorse became the language of tires, seals, and hoses spoken the same way from one factory to the next. The difference this made in the field is hard to overstate. Maintenance became a plan rather than a plea, and mobility became a baseline rather than a bet. Behind the raw output was a quieter triumph, a web of plants and standards that transformed every bale into a promise that a motor pool could keep. By 1944, U.S. synthetic rubber capacity had climbed past 1 million metric tons per year, a number that represented not only reactors and columns but the logistics to feed and empty them without pause. In practice, this meant commanders could requisition tires knowing what would arrive and when, and factory foremen could cure to familiar curves without recalculating every lot, which is how consistency became its own form of speed. The tactical benefit was simple. Trucks rolled when they were told to roll, and aircraft taxied out with a margin of safety that did not depend on luck. Feedstocks, too, found their wartime rhythm. In 1944, approximately 64% of the nation's butadiene came from grain alcohol via quick-built dehydrogenation plants, bridging the gap until petroleum routes matured and ensuring polymerization lines never starved for the first monomer. Parallel investments added styrene units from firms like Dow and Carbide, knitting monomer production to polymer plants by rail and river so that a cracked exchanger or a flooded siding at one site didn't silence a distant kettle. This was design as strategy, redundancy by geography and interoperability by recipe. Standardization turned throughput into trust. Because GRS recipes, modifiers, and tests were coordinated across companies, a bale from Baton Rouge behaved like one from Akron, and that sameness let tire makers and hose factories run their presses and mills with confidence day after day. The effect compounded. Stable properties meant predictable cure times, predictable cures meant fewer rejects meant more finished goods per shift, and more finished goods per shift meant convoys and squadrons that could plan by the calendar and not by contingency. In the war's arithmetic, reliability was acceleration. Numbers confirmed what mechanics and pilots already felt in their bones. From the trickle of 2,241 tons in 1942 to the torrent of late-war production, the program's escalation created a buffer between frontline demands and home-front sacrifices, so that an emergency became an inventory and then a routine. Just as important, the structure that produced those numbers, government-financed plants, private operation, shared know-how, meant any improvement learned at one site echoed across the network by the next quarter. In that echo, an army found its cadence. None of this erased rationing, and that, too, was part of how victory works. Tires remained rationed through the end of 1945, a policy that conserved civilian tread so that military inventories stayed deep enough to ride through campaigns that punished rubber in heat, cold, and speed. Gasoline limits and the victory speed of 35 miles per hour persisted as long as needed, translating shorter civilian trips into longer military ones, which is how a nation transfers durability from one road to another. When rationing ended on December 31, 1945, it did so because output and capacity had made controlled distribution unnecessary, not because demand had slackened, which is the right moment for a policy to step aside. By 1944, the supply chains for GRS had grown so sturdy that mobility ceased to be a constraint on strategy and became its enabler. Quartermasters could plan tire replacement cycles by mileage instead of by prayer, and aircraft maintenance crews could order seals and bladders as consumables rather than rarities, because the items that used to live at the mercy of shipping lanes now lived at the mercy of timetables. As the plants multiplied and the recipes converged, the war's what-ifs turned into when, and the answer to when was on time. This is how endurance is made, not by a single miracle, but by thousands of identical bales arriving exactly where they are supposed to be, exactly when they are supposed to arrive. Even the bottlenecks taught useful lessons at speed. When finishing shops struggled to incorporate carbon black fast enough, producers began adding carbon black slurry to latex before coagulation in 1944, pushing reinforcement upstream and relieving pressure where the system had pinched. Process fixes like that did more than clear cues, they improved dispersion and tire life, which meant fewer field failures and more predictable wear in the places that mattered most. In a year defined by momentum, each solved bottleneck became another small engine of acceleration. By the time the front lines lengthened into the Rhine and the Pacific's arcs bent toward home, synthetic rubber in America was no longer a project, it was an institution. The plants ran as if they had always stood where they were built, the railcars came as if they were born for those sidings, and GRS ran through mixers and mills as if it had always been the industry's first language. Capacity and consistency had fused into confidence, and confidence, more than anything, is what keeps trucks rolling at night and pilots willing to try for one more mission. When victory came into view, it rode on the knowledge that tomorrow's tires already existed, and the day afters were curing as the convoy formed up. The decisive advantage was not just the reactors or the railcars but the way a democratic society arranged people, knowledge, and capital so that problems solved in one place became solutions everywhere by the next shift. Universities, petrochemical firms, tire makers, railroads, and agencies formed a mesh that moved information laterally, committee minutes, test methods, modifier data, so that GRS behaved the same in every mixer because agreement had been turned into procedure. The consortium at Akron and beyond wrote a common language of rubber under government sponsorship, and with each revision to recipes or analytical standards the network tightened until uniformity itself became a form of speed. Public financing through federal corporations and the Rubber Reserve Company pulled concrete and columns into being, while private operators ran the plants under shared specifications that made each site a repeatable instrument. This was social engineering as much as chemical engineering, and the participants understood it. The Patent and Information Sharing Pact bound lifetime competitors into a single research front, converting private breakthroughs into public baselines that any qualified crew could run on new steel in 9 months. Academic partners, chemists and engineers, plugged analytical advances directly into production committees, making Mooney numbers, Cure curves, and dispersion behavior part of a doctrine rather than a guess. Because the architecture rewarded interchangeability over prestige, the system preferred standards that traveled fast to secrets that aged badly. Workforce mobilization completed the circuit. Wartime industry widened its gates to millions of women, transforming who ran machines and labs, while new training ladders and shift systems made it possible to staff reactors and finishing lines around the clock. African American workers contributed across the chemical corridor, including at the wartime butadiene and chemical complex at Institute, West Virginia, though their roles reflected both participation and the era's racial barriers inside the plants. What held the production system together was not a single demographic profile but a disciplined routine that made skill portable and work predictable, shift after shift. Contrast this with IG Farben's concentration of power, where monopoly turned vertical control into a bottleneck for adaptation. In the Reich, knowledge tended to move up and down within a single corporate hierarchy, guarded by patents and policy, which slowed the lateral diffusion of fixes when conditions changed daily under air raids and shortages. The company's preeminence in chemicals produced technical achievements in Buna, but it also meant the system staked resilience on a few central organs that could not regenerate capacity or know-how quickly when cut. Antitrust and post-war scholarship would later treat the breakup as a case study in how concentrated control can dampen innovation and responsiveness even in a firm rich with patents. Labor systems widened the gap further. At Auschwitz-Monowitz, IG Farben lashed production goals to coerced and starving prisoners, a brutal formula that murdered people faster than process control could stabilize, and that never delivered usable rubber before the Red Army arrived. Forced labor made quality a casualty. Starvation and terror destroy the cleanliness, attention, and continuity that continuous polymerization needs, turning a modern factory into a machine for attrition rather than output. Where the American program trusted routine and reciprocity to hold standards, Buna at Monowitz tried to beat precision out of suffering and reaped breakdown instead of bales. The Allied model ran on transparency that could be formalized and taught. Committee charters, testing protocols, and siting logic were recorded and circulated so that every plant became a school for the next plant, and every solved bottleneck, carbon black handling, monomer purity, heat removal, propagated without delay. In that loop, culture and chemistry became one operation: uniform feed, uniform reaction, uniform output, uniform logistics. Even missteps were metabolized quickly because institutional design made learning a feature rather than a confession. The German model, by design, hid more than it shared. Within a fortress firm, secrets could be defended, but they did not compound fast enough to withstand a war that punished latency, and they could not be taught at the periphery in time to matter when rail lines snapped and utilities failed. When bombing made hydrogen or power intermittent, the absence of a broad, standardized peer network meant a broken organ starved the limb, and yields fell even when buildings still stood. A system that prized command could issue orders, but it could not mass-produce adaptation at the speed required. The human ledger tells the same story as the production charts. In the United States, a lawful regime of rationing, wages, and training fused with a cooperative research culture to build capacity faster each quarter until synthetic rubber became routine. In Germany, a monopoly's secrecy and a dictatorship's labor policy built capacity too slowly and too cruelly to survive shocks, leaving impressive plants that could not outrun their own premises. Modern war judged both models and chose the one that made knowledge a common good and labor a dignified craft, because only that model could make tomorrow's bales arrive exactly on time. The lesson is not just moral, it is operational. Open standards, shared methods, and inclusive staffing do not merely sound better, they scale faster, repair quicker, and survive surprises with less drama. Monopoly and coercion can build walls and buy machines, but they cannot teach a continent to work in unison at industrial tempo, and in the end tempo is what wins when the front is 1,000 miles wide. In the war for mobility, social design was the master process parameter, and democracies set it to continuous. Victory did not silence the reactors overnight, it taught them a different song, as plants that had made GRS for convoys and self-sealing skins were retooled for peacetime tires, belts, gaskets, flooring, and wire insulation, the everyday elasticities of prosperity. The government owned the backbone of that system, and in 1953 Congress passed the Rubber Producing Facilities Disposal Act, setting in motion a deliberate transfer that would move the plants from federal hands to private industry once the national emergency had passed. By late April 1955, absent congressional disapproval, the Disposal Commission's contracts took effect and the synthetic rubber facilities passed into private ownership, formalizing what the wartime partnership had always implied: this was an industry, not a temporary miracle. The ACS landmark account is terse but decisive about the handoff. GRS production returned to private hands in 1955 when the government sold the plants, the moment a mobilization matured into a market. The transition was designed rather than improvised, and even the research pipeline found a steward. The Disposal Commission recommended that portions of the government's synthetic rubber R&D, university contracts and the Akron laboratories, shift under National Science Foundation supervision in a trial period through fiscal 1956, preserving technical momentum while industry absorbed physical assets. In practice, this meant that the knot of committees, methods, and test standards forged in war would not simply disappear. Instead, their functions would migrate into institutions that could carry them forward in peacetime. The decision recognized that knowledge is infrastructure, too, and that a supply chain of ideas requires ownership as careful as any of pipes and presses. Rationing had already signaled the turn from emergency to sufficiency. On December 31, 1945, tire rationing ended, with production rates judged high enough to serve civilian and military needs without controlled distribution, a pivot reported as a policy decision justified by output rather than by wish. What had been the first non-food item rationed in the war became the first reclaimed for a consumer republic, and the news read like a translation: inventories had replaced anxieties. The convoy's tires, the symbol of wartime certainty, became the commuter's tires, the family's tires, the open road's tires, a peaceful absorption of a wartime achievement. As markets globalized and the post-war car economy swelled, the material story bent toward continuity more than rupture. SBR, the civilian name for wartime GRS, remained the general-purpose elastomer for tires and countless industrial uses, consuming shares that exceeded all other synthetic rubbers combined and anchoring the industry's everyday recipes. The U.S. International Trade Commission's summary tracks a sector that kept expanding on new feedstocks and process refinements, but still measured itself by the reliability that wartime standardization had made habitual. When chemical engineers speak about interoperability across suppliers and plants, they are speaking a language that GRS wrote. The balance between natural and synthetic swung decisively in the latter's favor over the ensuing decades. By the early 1970s, synthetic rubbers accounted for more than two-thirds of total elastomer consumption worldwide, a structural shift that reflected both cost and performance gains, as well as the vulnerability of plantations to storms, disease, and geopolitics. That ratio has remained resilient, with modern industry references framing synthetic as the majority share of global rubber use while natural anchors critical performance niches, especially in heavy-duty and aircraft applications. The wartime wager, that chemistry could be industrialized into dependable mobility, became an ordinary premise of manufacturing. Even the names changed without losing their lineage. GRS shed its government designation and lived on as SBR, divided into emulsion, ESBR, and later solution, SSBR, processes that offered better wet grip and lower rolling resistance for tires chasing safety and fuel economy. Cold emulsion methods, seeded in the war's race to improve wear and low-temperature properties, entrenched themselves in post-war practice as producers chased tighter molecular control and dispersion. A material born of urgency found its way into the patient craft of saving fuel and stopping shorter on rain-slick roads. What had been an emergency scaffold of public capital and private operators became a matured competitive industry with global footprints. North America's share of synthetic rubber production fell from post-war dominance as Western Europe and Japan ramped in the 1960s, but the architecture of dispersed plants, standardized specs, and rail-to-press logistics remained the model everywhere it traveled. In an irony the Buna planners could not have intended, Germany's post-war chemical sector would operate inside markets where competition and diffusion, not monopoly, rewarded speed and adaptation, a lesson carved in the ruins of centralization. The breakup of IG Farben and the spread of know-how across firms made innovation less a secret and more a race, the only kind of race chemistry tends to reward. Legacy carries shadows as well as light, and rubber towns reckon with both. Akron's proud wartime output left a toxic footprint in soils, waterways, and lungs, a story of solvents, soot, and slurries that communities and regulators have worked for decades to remediate. Industrial abundance bought victory and prosperity, but it also wrote environmental chapters that later generations would have to revise with new materials, cleaner processes, and stricter rules. Even that reckoning is part of the inheritance of standardization. When a problem is common, solutions can scale. The arc from barbed wire and convoys to white walls and factory floors bends toward a simple continuity, the same design principles that won a war, open standards, coordinated finance, interchangeable parts, and predictable quality, won the peace by making mobility ordinary. In 1955, when the plants passed into private hands, it was not an end but a transfer of custody, a recognition that the engines of reliability had become civilian institutions. And today, when a truck rolls off a lot on SBR treads or a conveyor belt flexes hour after hour, it does so on the same quiet premise that carried a nation through 1944, that rubber will be there, uniform and on time. The convoy, at last, belongs to everyone, and its rhythm is the sound of a solved problem carrying the weight of an unsolved world.